Welcome to Calculus. Being challenged has a whole new meaning. On this episode, Stevenson will demonstrate So Newton and Leibniz were able to model things that are constantly in motion using something called a differential equation. So this is an example of a differential equation. Now what we're going to learn though is how can we figure out what is a possible function that this differential equation came from. In other words, what is its antiderivative? So when you solve differential equations, there's two possible outcomes. In this first example, I want to show you what's called a general solution. So this is asking us to find all the possible functions y that satisfy this derivative. So essentially what we want to do is our function y is going to be the integral of r dy dx. So let's use our antiderivative rules like reverse power rule here, and then the antiderivative of secant squared we have to know from our derivative of tangent rules. We need to add plus c here because this function, if you take the derivative of this, you will get this differential equation exactly you see here. The problem though is this is a function family. So in other words, this is a family that has this exact function, but it all differs by a single constant. If we take the derivative of this constant, we will get 0, and thus we will get this differential equation. You must have a plus c on your general solution. Let's look at another example. In this case, it's asking for the particular solution that gives this exact equation, but they're telling us a clue about where this derivative is coming from. The graph of that function from where this derivative comes from passes through this point. So this is what we call an initial condition. So when x is 1, y is 0. So the first step is we need to come up with the general solution. Then once we have the general solution, we're going to use this initial condition to solve for c. Then we'll know the particular solution. So first let's find the general solution. So what I did there is I did reverse power rule, and then the derivative of e to the x is just e to the x. So that means its antiderivative is itself. Now we're going to use this initial condition to find out what c is. Now when you do this, you don't substitute anything in for c. Remember, that's our goal, is to solve it. But what I'm going to do is I'm going to substitute 1 in for x and 0 in for y anywhere I see them in my general solution. Now I'm just going to solve for c. Now that I have my c value, what I'm going to do next is just rewrite my general solution as a particular solution with my c value. Let's look at a third example here. So again, we're going to find the particular solution to the differential equation, dy dx equals this. And then again, we have an initial condition. Notice the structure is given to us a little differently. So the first step is to find our general solution. Okay, so here's my general solution. Now I'm going to use this initial condition. I had a few mistakes there, but I forgot to substitute 0 here. But regardless, I cleaned it up, so c is 3. So now let's write our particular solution. There's something I want to point out here. This function has discontinuities. Its domain is not all real numbers. So this particular solution is only valid over a very strict domain. Tangent function is bound. It exists every pi, but it has vertical asymptotes. It is discontinuous at certain spots. It has vertical asymptotes, which makes it undefined. So if we look at this point, x equals 0 is right here. So that means this particular solution is only good for this piece that exists over this domain. It is not good for the entire all real numbers domain. In the previous problem, if you look at it, you end up with an e to the x, its domain is all real numbers, and you end up with a polynomial. Again, its domain is all real numbers. So there's no domain restrictions. This one here, we ended up with a polynomial, domain's all real numbers, but we ended up with a tangent. It has domain restrictions. So we look and see, where does this x value exist within the tangent function? It's in this interval of tangent. Therefore, this particular solution is only good over this domain. That is it.